Okay, can I start sharing the screen?
Yeah, the floor is yours. You can start. You are free
Okay.
now. Yeah.
All right, can you see the screen and the presentation?
Yes, we can see it very well.
Okay, great. So hello everybody, I'm Tommaso Dolci. I'm an assistant researcher in Politecnico di Milano University. And today my presentation will be on word embeddings and the huge topic of ethics in natural language processing. So this is the outline for the presentation. We will start from a brief introduction on the topic and then move on to the big problem behind natural language processing from an ethical standpoint. We'll see quickly some background on the literature on how researchers in the past measured and tried to mitigate the problem of social bias in natural language processing. And then in the second part of the presentation, I will present some of my works from previous years on, again, measuring and mitigating gender bias specifically, and for sentence encoders, which I will tell you later what I mean with sentence encoders. So starting from an introduction, I'm sure you are all very familiar with pre-trained language models nowadays. It's a huge topic. Of course, we mean that these are computational models that are intended to give semantic representation of natural languages, such as English or Italian. And this semantic representation means we want to represent in computationally, so with numbers, the meaning of words and sentences. And these models are usually pre-trained, which means that these big tech companies like Facebook or OpenAI or Google, they take very big corpus of data, of textual data, that they take usually from web sources. And then they do this training of the model for very generic natural language understanding tasks. And then subsequently, if you want, you can take the pre-trained model and then do some further training to improve some specific aspects of the model, such as improving, for instance, the semantic understanding of a certain field like healthcare or business. And nowadays, most of the language models are based on embedding techniques, which means representing words or sentences, in general, representing languages with vectors and with geometric representations, let's say, numeric geometric representations. So embedding models can be classified in different ways. For instance, we can have classification based on the granularity of the representation. We can talk about word embeddings, which represent words from vocabulary, from a language. We can have representations of sentences. We can even have representation of entire documents, even if this is a little bit like old thing that they tried. Nowadays, it's not very popular anymore. And moreover, we can also identify two different classes of word embeddings that are based on the nature of their representation. So either static or contextualized, which means static embeddings are like a dictionary. You have the word and then the vector representation that is always the same. As for contextualized embeddings, you have some preliminary representations in the model, and then the actual representation depends also on the sentence where you're using the word. So it depends on the context of the sentence. So it's very good for synonyms, for instance, because synonyms can have different meanings wait, no, not synonyms, but words that have different meanings. I don't remember quite the name in English. Written the same but with different meanings, which depend on the context. So they're not synonyms. They look the same, but they actually have different meanings. So more specifically, word embeddings are vector representation of words, which means that you have a multi-dimensional space, vectorial space. Inside the space, with all these dimensions, you can identify coordinates and points, which are actually like vectors in this space. And each word of a certain language is identified uniquely by a certain point in this space. And this means that these models translate the semantics, so all the meanings of the words, into geometric properties. And so are geometric also the metrics that are usually used to estimate similarity between word vectors. And one of these, like the most common and famous one, is cosine similarity, which is based on the angle between two vectors. And this is like the formula is quite easy actually. And intuitively, you can have, let's say, three more or less scenarios. So you can have two word vectors that are very similar in their meaning, and their angle, the angle between them, as you can see in the bottom left corner, is approximately 0. This means that a cosine of the angle is approximately 1, and the correlation is between the cosine being 1 and the words being extremely similar in their meaning. As the angle reaches 90 degrees, this means geometrically in these models that the meaning of the words represented by the two vectors are opposite. So they are contraries. And if you have the very interesting case of two word vectors that are more or less on the same direction, but they go on different sides, so the angle between them is approximately 180 degrees, and the cosine is equal to -1. This means that the two words are extremely correlated between them from a semantic point of view, but they represent in some way like opposite concepts. So they're very correlated, but they represent opposites like male and female, so two different concepts inside the same semantic area. Moreover, it is possible to identify clusters in this vector space based on the semantics of the words represented by the vectors, as you can see in the image. And as for sentence embeddings, which are a big thing nowadays too, we have a similar idea. So the idea is to have vector representation, but this time not of a single word, but of an entire sentence. And all the time, the so-called sentence encoders, which means models that encode, so produce vector representations of natural language sentences, they always start from word level representations. So in the past, for instance, researchers were taking static embedding models at word level and then doing some average or summing together all the word vectors of the words inside the sentence. and just produce a very simple sentence level representation. Of course, this had very, like many drawbacks. For instance, if you have two sentences that contain the same words, but arranged in a different way, then the average is the same. So this was the main reason why a lot of researchers invested in producing models for contextualized embeddings. So if you contextualize your word embeddings, you look at the whole sentence, but also the position of words inside the sentences. And in this case, if you then take all your word level representations and you average them together for a sentence, you will have different sentence encoders, different sentence embeddings, different representations, even if you have two sentences that have the same exact words in them, but arranged in a different way, because you take into consideration the entire sentence and the entire context of the sentence. So some examples of encoders for natural language sentences are sentence BERT, which is based on BERT, or infercent, which is based on GloVe. And usually these kind of models for encoding sentences are extremely complex and based on deep neural networks with many different layers. And the same applies to sentence embeddings. So you have many geometric properties between sentence representations. You can use the cosine similarity. You can find clusters inside the vector space. So it's basically the same. You just have a representation for a sentence instead of a single word. So now that you have some of these preliminary notions, we can further move on to the problem. So as we were saying before, the context is that language models today are used in widespread. They're used for many different tasks in many different situations. For instance, we talk a lot about ChatGPT. It's very popular, and it's based actually on GPT, which is language models, the language model by OpenAI. And ChatGPT is more on the generative AI side. So it's very, very advanced, but actually in many different scenarios, such as in industry, but also in research, depends on the field, more traditional embedding models are used. So ChatGPT is extremely complex. It also has the interface, but GPT itself is very advanced and complex models. But actually also more primitive embedding models are very, very common to be used. For instance, in the healthcare scenario, you can use static embeddings and they work very well. You don't need models based on deep neural network architectures. They are usually more advanced, but also slower. So if you don't really need them, you can just stick to static, simple embeddings. So the problem is that you have this pervasiveness of general purpose language models for many different supporting tasks or advanced tasks, also applications with the human-computer interaction side, such as chatbots. But the thing is that it has been demonstrated that applying machine learning without really taking care about your model, about your training data, especially, runs the risk of amplifying social biases that are already present in the data. So the actual problem that we see today is that language models are widespread, but frequently they internalize a representation of society that they take from training data, and that is not really an ideal representation. It's usually a representation that is centered on males, centered on white people, It's centered on the Western society in general. And these can be extremely discriminative. For instance, if you take the case of CV parsing using automated decision-making AI-based systems that are based on language models, what do? They take your CV, they screen it automatically, they look at the words and sentences that you wrote on your CV, and then they extract correlation between a description of a job and your description of yourself and your career from your CV. But for instance, if you have in your AI model, which is based on these language models, a strong correlation between certain jobs and certain ethnicities or a certain gender, then your automated decision-making system will make these associations. So for instance, males are usually associated to engineer or computer science jobs. And if you take training data that actually does not care about the fact that computer science is a field for everybody and not just for males, then what happens is that CV parsing based on such systems can make this association, which is stereotypical and it's untrue. But what it will suggest is that a male candidate is better suited for the job than a female candidate. And of course, we do not want this. And it's quite a big risk for society. And nowadays that these models are extremely popular and becoming more and more popular, actually, the social risk is also increasing. So as I said, the problem is the misrepresentation of minority groups that causes this so-called social bias. And of course, it runs the risk of strengthening discrimination for social groups that are already frequently penalized in our society. So let's now go to like a quick background on literature. So it is quite a recent topic, the one on social bias in language models. It started in 2016 with the famous paper, Man is to Computer Programmer as Woman is to Homemaker, where the researchers found that there are this kind of correlations inside language models, so that if you ask for analogies and you say man is to something as woman is to something else, your language model will reply with man is to programmer as woman is to homemaker, because the correlation is that males should work as programmers, but women should stay at home and not actually do any sort of work regarding programming or computer science. So this, of course, is stereotypical and absolutely wrong. But this is what emerged from the actual geometry of language models. Specifically, it was word-to-vec trained on a lot of data from news and newspaper sites. So actually, it was like sort of controlled training data because it was written by experts, it was written by journalists. But still, it's not very easy to avoid like stereotypical correlations, because bias are usually historical. So we need to be extra careful about it. And how did this researcher actually measure gender bias in their work? So what did they do is to, as I said, take this word-to-vec model, which is a static word embedding model, But the same applies to, for instance, GLAB, which is another static word embedding model from Stanford. So what you do is to identify a direction, so a sort of subspace in your multidimensional vector space that represents the embedding model. And you look at all those words that should be gender neutral. So for instance, programmer should be gender neutral. So if you say programmer, you don't know if it's a male or a female that you are talking about. And the intuition is that gender neutral words should be orthogonal to the gender direction. So it means that they do not have any correlation with gender. And of course, this was not true, but you can measure the amount of bias by taking a lot of these gender neutral words, and then you look at the similarity of each of them with respect to this gender direction. Because causal similarity is a metric, so it's something that you can compute, and it has a numerical value to it. And this way you can measure just by taking this cosine similarity. Of course, this is a little bit more difficult for contextualized embeddings. Why? Because it's not like a dictionary. Like contextualized embeddings do have a sort of like underlying representation of words, but then the final representation depends on the context. So it's not super easy. And the same applies to sentence embeddings, because as we saw before, sentence embeddings are produced starting from word level embeddings, usually contextualized. So if we have a problem with contextualized word embedding, we have a problem with sentence embeddings as well. This approach was then later adapted to also ethnic and religious bias, and it works pretty well, but again, only for static embedding models. Then, like other researchers introduced another way of looking at the problem, and introduced in particular the so-called word embedding association test, which measures the amount of association between given target concepts and given attributes. You can see it at the bottom of the slide. For instance, you can take some European names, typically European names, and some typical African names. Then you can take some pleasant concepts and ideas called attributes, and unpleasant ones. And then you look at the similarity that you have between the concepts and the attributes by crossing them together, and see if there is more correlation, for instance, between the European names and pleasant attributes and African names and unpleasant attributes, which of course represents a serious ethnic bias and social stereotype, historical social stereotype. The same can be done with sentence embeddings, just by extending this test and substituting single words with actual sentences. But we need, in this case, to be careful to not have any sort of context. Otherwise, the context of the sentence can have an influence, an impact on the whole representation. And of course, again, both tests demonstrates the presence of human-like biases, especially concerning gender and ethnicity. So a further step in literature was to try and, let's say, try to solve the issue by mitigating the amount of bias in this model. So one thing that was proposed is to take your word embeddings and do this hard biasing procedure, which means, as you can see on the right, to rebalance the vector representations of your gender related words, such as actor and actress, so that they are now equally distant from the gender direction. And the second thing, for all those gender neutral words, you take the representation and then you neutralize the components on the gender direction. So it means that you are in some way removing geometrically the semantics of gender from any word that should not have any gender connotation, such as receptionist in this case, which is a job and should not have any gender connotation. So by equalizing and neutralizing, you in theory should obtain an idealistic model that does not present any gender bias. But actually, what is being demonstrated is that language models are more complex than this. And even if you equalize and neutralize them, still, for instance, by clustering, you can still find some stereotypical associations. So if the next step was to try and stop working on, let's say, solving the problem in the final model and try to look in one step before in the training pipeline and to try and improve the training data. So try to have, by data augmentation, for instance, better training data that can solve the problem of misrepresentation of minorities and different social groups. As for sentence encoders, so models that produce sentence embeddings, what has been seen is that adopting the hard biasing procedure is not really possible, because hard biasing only works for static embeddings when you do have a limited amount of words. So you can take the vector of every single word in your vocabulary, in your language model, and then do the neutralization or the equalization, depending if it's a gender neutral word or not. But you need a very, very limited, you need a limited amount of vectors to work on. If it's unbounded, if it's an unlimited number, then this is impossible, because how do you retrieve them? So if the representations are produced at runtime, as is the case in contextualized word embeddings, this is not truly possible. You can still think of removing it, like do this neutralization or equalization at runtime, but the problem is, for instance, that certain sentences do contain both correct gender semantics and like sort of stereotypical gender semantics. So the sentence, my mother is working at home, is stereotypical, because you assume that females work from home, work at home, and males do not. But actually, in the word embedding of mother, you do have correct gender semantics, so you do not want to remove it. And so the thing is that in literature, those researchers who tried to apply hard biasing, especially to sentence embeddings, they obtain very conflicting results. So other people suggested to try pre-processing techniques. So again, working on the training data and not on the output of your model. Other people are just thinking that the more we go on with the research in natural language processing, and the less this problem will be. So the problem will solve itself, let's say, with better architectures and better neural networks, better training data, bigger training data. But this is, let's say, not really true, and there's many pitfalls in this reasoning. So just to say one, thinking that in the future we will solve this problem just by making better architectures disregards the problem currently. So we have the problem today, we should try to solve the problem today and not just hope for something better in the future. So the problem is now, let's say. So this second part, after the introduction, after the problem statement. So the problem statement is that language models are widespread and very popular, but of course they present some problems of representing social groups and social minorities, and they do exhibit stereotypes association. We saw that in literature, we have some works on both measuring and mitigating bias. We can measure it in a really good way, let's say. We have different ways of measuring bias, but mitigation is not really working very well. And moreover, we have some problems with sentence embeddings, because of course, static word embeddings is quite easy to do all these procedures. You have a very static model, it's easier to look inside. Contextualized word embeddings are a little bit more tricky, but you can assume that your procedure can be the same as with static word embeddings with some limitations, but with sentence embeddings, the thing is more difficult. And so this second part, as I was saying, I will present some of the works that I did with other colleagues here in Politecnico di Milano to try and tackle this problem of measuring and mitigating bias, and specifically gender bias in sentence encoders, so models that produce sentence embeddings. So the research question is the following. So we saw that we can use cosine similarity or other geometric matrix to estimate similarity between word vectors for gender neutral words and the gender direction in the vector space of these models. But this traditional approach does not work for sentence embeddings. Why? Because first, sentences are infinite in number, so you don't have a limited number of sentences. You can have any kind of sentences, and so it is not possible to say, okay, I take a model and I measure this gender bias, taking the cosine similarity of every single sentence in the word. It's impossible. You can do it with words, but it's not possible with sentences. So we need to do something at runtime, let's say. And the second problem is to try and separate, as I was saying before, the amount of correct gender information. So gender information, gender semantics, that is from correctly gendered words like mother, female, he or she, and separate it from the amount of gender information that is, let's say, false information, and that is coming from gender biased words. So stereotypical concepts, for instance, like programmer, as we said before, or homemaker. So these are just two examples. Usually, very frequently, jobs are very, very stereotypical in some way. Also, sports professions, you have volleyball is considered more for females, you have football more for males. So these are the gender neutral words that actually in language models are very much biased. So the research question is the following: how can we effectively measure gender bias in vector representations produced by sentence encoders, so in sentence embeddings? And then, of course, also how to try and mitigate this bias. So what we need is to start from the literature and the traditional approach for measuring gender bias. We said before that what we need is to measure bias using the cosine similarity. We can use this metric, and in particular estimate the similarity between neutral words and a gender direction. However, for sentences, it is not possible to have a list of sentences because they are infinite in number. We can still retrieve a gender direction. It works really well. The approach is still valid. And we said cosine similarity is still a very good metric for semantic similarity in sentence embedding, for sentence embedding representations. And this is the second problem. So one is we cannot have a list of neutral sentences or gender sentences. The second one is that some sentences are explicitly gendered, like my mother is there. Some of them are completely neutral. So like someone is a nurse, this is a neutral sentence. Of course, these are those kind of sentences that are more prone to be biased, especially with like professions such as nurse. But then sentences can also combine explicitly gendered words with neutral words. So if you have the sentence, my mother is a nurse, how can you measure the amount of gender information that is correct from the one that is not correct? So of course, this sentence may be, again, biased, but it's not easy to measure the bias. So this is an example of measuring similarity, gender similarity, using cosine similarity with respect to a gender direction. We were taking two sentence encoders. One is infant and the other one is sentence birth. And as you can see, of course, we have my mother is there, which has a lot of gender information, but it's correct because mother is a female term. Then you have in the bottom, someone is a nurse. Again, in this case, we have some gender information, but in this case, is not correct. It's determined by bias because it is supposed to be a neutral sentence and a neutral concept. And then if you combine them together, you have my mother is a nurse, but again, you have a lot of gender similarities, so a lot of gender information, but it's not easy to distinguish the amount of gender semantics that comes from mother and the one coming from nurse, because this is a non-neutral sentence that again can be biased. So at the beginning, what we try to do is to adopt the traditional approach for measuring gender bias in word embeddings, and to do so in a way that we can apply this approach also to sentence embeddings. So we start again from these three main things. We have gender neutral words, which are very important. Of course, we have cosine similarity as a metric, and we have the gender direction. These are our three ingredients. And what we do is to look at the gender bias at word level, because we start from the assumption that bias is something connected to semantics, and semantics in linguistics in general comes from words and not from like sentence in its entirety. And what we do is to try and add this word importance that is an additional ingredient to try and insert some semantic related aspects inside our final result. And so what we obtain is a score that we name bias score that allows to do some estimation of gender bias also for sentence representation. So this is the general flow. We start from these are the three main ingredients. We start from the input sentence. We have our sentence encoder, which always presents a pooling layer. Can be a max pooling layer, can be a mean pooling layer, which combines together the word level representations. So what we do is to keep the word level representations, and then from the pooling layer, we extract this semantic importance, which is based on the number of times that specifically with max pooling, you select a certain a certain embeddings. Your encoder selects a certain embeddings. So if the embeddings of a certain word is selected many more times in the pooling layer, then this means that this word is more important for the final representation. And then by combining these word importance, the word level embeddings, gender words, and gender direction, we can estimate the gender bias on both directions. So these are the elements involved that we saw previously, just in a more formal notation. This is the model that we did some experiments on, which is InferCent. InferCent is more convenient than other sentence encoders because it uses as preliminary word representations those from GLAV, which are static, and it adds some contextualized, some contextualized meaning thanks to a bidirectional neural network that ends up in this max pooling layer, which is also good for our approach. And then after pooling, it creates this final sentence embedding. So pooling means that you take, in case of max pooling, the highest value among, like okay, I mean, it's important to clarify this. So in this case, let's say you have 4 embeddings, 4 vectors. And let's say each of the 4 vector, it's made of like 5 or 6 dimensions. And for each dimensions, so you take all your vectors, and you look at the first number, which is associated with the first dimension, you take the highest. So this is basically max pooling. Then you go to the second one, and you take the highest. So the highest number in the second position of all your vectors that you are considering. And mean pooling, it's even easier. You just take the mean. So you do the average of, let's say, 5 or 6 vectors together. Okay, so the thing is, InferCent is also quite convenient because it's trained with supervised learning on a relative, like it's very big, but it's still a relatively small corpus of text, which is called SNLI. So the stands for Natural Language Inference Corpus. So a little bit more on gender direction. How do we achieve this? Like, how do we obtain this gender direction? So we exploit the PCA procedure by taking a certain number of gender words and pairing it with the opposite pair. So for instance, if we take she, which is a female word, we then pair it with he. We take the vector representations of the two. We then make a subtraction. By making a subtraction, we obtain another vector, which goes from one, so from the first of the two vectors to the other. And this is actually a direction that connects these two words. And then you can repeat it with other pairs. So you can take female, male, you can take mother, father, and then do some averaging. And this average is made by the PCA, more or less. So what we try to do is to use a lot more pairs than literature, and then apply this also on a sentence level. So we looked, as you can see on the right, at, for instance, same thing, but with sentences. You have pairs of sentences with female and male subjects or terms, and then you do exactly the same thing, and it works really well. So this is what I was saying to you before on word importance. If you are more interested, you can then look it up on your own on the slides. And this is one example of word importance. So as I said, it empirically works really well. So you have, for instance, in this case, saxophone is the less common word in the sentence, and it is the more important one according to this pooling procedure. So this is the actual algorithm, like formula. And as I said, we obtain bias score in the two directions. So you can estimate the female score and the male score, or you can also take the absolute value and sum everything together to obtain like one single bias score that doesn't tell you if it's in a female or male direction. So if it's a female stereotype or a male stereotype, it just tells you that it's very biased sentence. This is one example. So as you can see, we have the sentence, she likes the new pink dress, which is a stereotypical sentence. So what we do is to consider the importance of the words. We see that the more important words are adjectives or nouns. And then we set at 0 the gender bias for any gender explicitly gendered words. Why? Because this is correct gender information. So for us, it's not biased. And for the rest, of course, you have an amount of bias that intuitively it's higher for stereotyped conceptions. So in this case, the color pink is more biased. So the word vector for pink is more biased, and the same for dress. And then you can take everything together and compute the female bias and male bias. And in this case, you can see that the female bias is very, very high. And the male bias is like very, very little, because it's actually a very female stereotype sentence. So what we then try to do is to also mitigate the amount of gender bias, but we did so by looking at the data, because this seemed to us the best way, because we saw before in literature, some people try to neutralize bias, but then some other researcher discovered that actually you were just looking at one side of the problem and not every single side. So we look at the data, because data is central in any machine learning and deep learning algorithm model. So the intuition is that the gender bias comes from internalizing gender stereotypes, which is very intuitive. So what we try to do is to use this bias score to identify sentences that are more stereotypical. So they have a bigger and higher bias score because they contain stereotypical conceptions and associations. So if we remove these kind of sentences from the text corpus, we can effectively obtain a more fair corpus of training than if we do retrain our model and we use the inference because the training phase is quite long, but not too extreme computationally or from a time point of view. So we should obtain also a fairer model. So this is the intuition. We want to keep the same quality, and we look at Centeval, which is a tool for estimating quality of sentence embeddings, and then we want less bias. And so we use this sentence encoder association test that look at stereotypical associations inside a model. And this means that if we have same quality, at least same quality, less bias, we have a better model. So this slide is on SNLI, the for natural language inference corpus or dataset. If you want, you can also search it online. It's from Stanford, this corpus as well. And this is, let's say, pipeline. So we have our corpus. We want to estimate the score, the bias score for every sentence in the corpus. And then we either perform some data augmentation or data subtraction to the corpus to obtain a fairer version of the corpus. We then perform retraining of this improved version of SNLI. This gives us a new encoder, and then we test the encoder with Centeval and CIAT. So these are examples of bias score from sentences in SNLI. These are the highest male biased sentences in the corpus and male bias. So as you can see, we have, for instance, some colors or dresses are usually certain colors and dresses are associated to females, and then you have a lot of sports associated to males like football and baseball. This is the distribution of bias score. So we have not so many high biased sentences, but what we did is with these sentences on the right of this red line, which is a threshold, we removed those sentences, or we tried to rebalance them by adding more sentences with counterfactual associations. And we tried to do so with different thresholds to look also at how it changes with different amount of mitigation, let's say, with different amounts of mitigation. Yes. So especially for, removing is quite intuitive. So we took the highest biased sentences and then we remove it from the corpus, and that's it. But for augmentation, it's not so easy. What we did is to swap all gender words with the respective, like from male to female, from female to male. So with the respective counterpart. And we did it with not just nouns, but also names, a lot of names that we took from like American lists of names. So these are just few examples of duplicated entries for data augmentation. And what we obtain is that in every single of these cases, we have a fairer model compared to the original. And especially for augmentation, we can see that the higher is the mitigation, and the lower is the stereotypical associations identified in the models. And for subtractions, it's kind of like it's still lower, doesn't have a monotonous, some monotonous, but still we obtain better results. From the quality point of view, we were more or less the same. So the original obtained a almost 80 score in this Centeval average overall score, and we are not far off. We also tried at the bottom with other approaches from more traditional approaches from literature, and as we can see, the problem was that even if they worked quite well for fairness, but they really did degrade the quality of the sentence embeddings. So we think that our approach is more consistent. Okay, so this was all done on Infercent, which is based on static word-level embeddings, but we also extended the same approach to contextualized model, and it doesn't change much, actually. We can still find the gender direction in, for instance, sentence encoders like SemPlusBERT, which is based on BERT, that is a word embedding model from Google. We can perform the PCA. We can find the gender direction. We can have our gender word importance. Word importance does still work, as you can see on the bottom right. And this is an example. It's the same as before. And again, we do look at the results, and you see that we have still a lot of female bias. In this case, it's all female bias, and it's quite high for every single word. But why? Why? Because in this case, we have contextualized embeddings, and contextualized means that they look also at the other words in the sentence. And in this case, we have a female subject. So some of the gender information that is encoded into the vector of she reverberates into the vectors of all the other words in the sentence. So our approach is, it works, but it needs like an additional layer of reflection, because these are some other examples. We can see, for instance, that if we take a sentence that is a stereotype, let's say, because homemaker is a stereotypically female, but if we give to the sentence a male subject, then it appears that the sentence is male biased, which is maybe not really true, because we expect the opposite. But then if we look also at the same sentence with a female subject or with a neutral subject, then we can really see how the model works, in the sense that the amount of female bias that we have with a female noun is a lot more higher than what we can obtain as male bias with a male noun as a subject. And moreover, if we take a neutral subject, and we should have a completely neutral sentence vector as a result, we can actually see that the result is not neutral. So from this, we can understand that our approach, it's okay, but it's especially good for contextualized embeddings when we have very totally completely neutral sentences, and not sentences with explicitly gendered subjects. And then we did some more experiments. For instance, if you take longer sentences, of course, the context coming from a gendered subject will not be as important, because it gets diluted in the overall context of the sentence. But what we discover in general is that bias is still present. So again, if you compare this set of sentences, you can see that we have very high female bias for this stereotype, like female stereotype sentences. And this, even if you change the subject and put on a male subject, the context is in some way more male oriented, but still we have a lot of female bias because it is coming from stereotypical associations from the rest of the sentence. And so to conclude, what we saw today is that word and sentence embeddings are very, very popular, are used for many applications. They're pervasive and widespread, but they do contain gender bias and other kind of social bias. It's the same. it's exactly the same. And this comes from internalizing social stereotypes, which are embedded in society. And nowadays, there's a lot of research on both bias measurement and mitigation in the field of computational linguistics. But as we see more complex and advanced models and sentence encoders in particular, they poses many challenges from a methodological point of view. So we need some more research in this. But what we discussed today, it's bias scores, a new metric that actually works for measuring gender bias in sentence encoders, which is something that literature did not achieve before. We also see that we can see that our retraining procedure actually reduces gender bias, even if it's quite computationally intensive and probably not applicable for very large pre-trained models. But finally, we also looked at contextualized embeddings to see that by reasoning on the results of applying certain gender bias matrix, we can still see that the problem is there, and we should at least be aware of it. So thank you for your attention, and if you have questions, I'll do my best to answer them.
Thank you very much, Thomas, for your interesting presentation.
Thank you.
Please questions and comments.
Okay. Yeah, if anybody has questions, you can talk.
By the way, have you done some complexity evaluation of your model? I mean, the infer set, I guess.
You mean how much is computationally intensive to
yes.
do all the?
Yeah.
Well, we did not do like a proper performance evaluation of this like retraining task or even like bias score computation. But I can tell you that retraining InferSet was taking like approximately 8-9 hours with a good GPU, not amazing GPU, but still good GPU. So it's quite computationally expensive. And also estimating gender bias for a big chunk of sentences, for instance, all the sentences in SNLI, it's actually quite expensive computationally. We did it on Google Colab using their GPU, which is very good GPU, like NVIDIA Tesla P4, and so very good. But it was taking like 1 hour with a very good GPU. And SNLI, it's a big corpus, but it's only, let's say, only around 2 million sentences. So it's not like huge, it's just very big. So it's quite computationally expensive.
Thank you very much.
Any other question?
Well, I guess there is no more questions. So once again, thank you very much for your presentation, and I wish you a very good career. Yeah.
Thank you. Bye. Bye.
Bye. We can end the presentation. Thanks. Bye.